We'll ask them all to come down and accept a diploma and also a small prize, and then they will get a small prize. So the first winner was David Velasco Villa Lizardo. So it comes with a diploma and an envelope which contains, unless you drank more than 50 beers, you have to pay the bill. So that's congratulations. Thank you.
Very convenient to present my work. My name is David. I have been studying a doctorate degree in Brazil, in this university, Federal Santa Catarina. I will show you from Colombia, but I live in the southern part of Brazil. This is a kind of picture of my work group, and there are two foreigners, and one from Germany and the other one from Colombia. And this is a very interactive. This is my supervisor, and this is a kind of sakili, lots of spare sakili. That's for making the jobs. Well, I will start with this very known bomb in quantum speed limit. It's the first one. It's related to the inversely proportional of the energy uncertainty. There is another one. There is related with the microscopic beam. Yes, and this is related with the mean energy above the ground state. But we didn't have to start a discussion which of these two bounds are best. So we tried to define the initial state as a homogeneous superposition between two eigenstates. So these two states have the same weight, and we want to find which kind of system with two states we can just work it. The first purpose was the simple interaction with the spin and numerical magnetic field, but we noticed that if we can, in a classical way, the electron is moving. The electron have a trajectory that is a Hamilton motion. In quantum mechanics, we have almost the same, but the Schrödinger equation say that we can express the momentum just as a canonical transformation. We use the gauge, the Landau gauge, because this movement have a symmetry, an axial symmetry. We got this differential equation in which we have in z direction a plane wave, or perhaps a free particle, and we have a confinement and a harmonic confinement in x and y direction, and also the interaction with the speed, the magnetic field, and the reaction of the angular momentum in this direction of magnetic field. So we solve, our purpose is to try to express the wave function in three different components. The radial or the plane wave function. The free particle is z direction because it's all of the magnetic field. And the final one is the gamma, is the spin up or down. Something it's very easy, the canonical way. So first one, if we solve that kind of equation and using the symmetrical this kind of symmetry, we can apply the symmetrical coordinates. After all, we got this function. This is a radial function for rho and fixed, and the angle phi. Well, we got, after many steps, we got this is the radial function. This is a normalization part. It's so difficult to have many factorial. But the main idea is the function is dependent, or is written in function of the generalized Laguerre polynomials. And this is so strange. This part have a counterpart in optics, but I don't want to explain something with the time. The energy expression, we have the plane, the free particle contribution, and the other one is the harmonic contribution. And also we have the main quantum number, and also the ML is a projection on the angular momentum along the z direction. And remember, please, that the omega is the frequency of this harmonic confinement, invitational. This picture shows that this is the product probability density of every single state. We just plotted the first six identified eigenstates. We have the main quantum number, we have the projection on the angular momentum, and just defining which how can we find the first state as an homogeneous proposition, and which is the mean position of the electron, and to go to the orthogonal state, and which is the maximum displacement. After many steps, we got that the best possibility is to make this proposition from 0 to 2, or from 2 to 4, or just keeping the same party, the even party, but the angular momentum, the angular projection is 0. If I have many more time, I would like to explain why the M0 is the best option to do proposition in these states. So, just an example. We start with the ground state, superposed with the next state in the according to the party. The angular momentum is 0. Have the same projection of the spin, and this is the radial. This is the radial probability of every eigenstate. We have the energy for every eigenstate. In this case, it's an homogeneous proposition. Both bounds, Margolf and Modestin are the same, because the energy uncertainty is the same to this one. So we got the minimum time to evolve the initial state and reach the other orthogonal state completely. This time is inversely proportional to the magnetic field. So we have the initial state and the first time 0, the electron is located like this in the middle position. The orthogonal one, the radial probability distribution, show us that the middle position of the electron is located here in this part. So if we calculate the maximum distance of this middle position to the orthogonal one, we have that this distance of displacement is inversely proportional to the magnetic field. So if we calculate this distance and we divide it by the time that we use it to do this evolution, we got a middle radial speed, in which this radial speed is directly proportional to the magnetic field. That means that if we have a very strong magnetic field, we could have a middle radial speed equal or faster than the speed of light. This is the value in which we can plot it at the same speed at the speed of light. But this is very strange, very strong, this just for this. The universe only starts, the neutron star perhaps has this very strong magnetic field. So, for the other hand, we have a direct description that is completely relativistic. The main difference is the Hamiltonian. It's expressed with another terms, but the other main difference is the quantum state expressed by using a spinor. The spinor have more information than the wave function in Schrödinger equation. We have the first part is for the electron, and the other part, the third and fourth, is related to the antiparticle of this electron. So this is the positron. And these two ones are completely relevant in two specific cases. We have a very huge momentum. It's completely relativistic particle. And the other one is when we confine a particle into a space very close, its dimension is very the same scale of the Bernoulli function. The other terms, it's comparable to the contribution for the electron. So the electron describes an homogeneous proposition with its antiparticle. And the energy, as I said before, we have the quantum speed limit, just calculating the energy uncertainty, and we put it in this expression. And we can notice that this expression shows us that beta is a constant. So the time of evolution is inversely proportional to beta. But beta is directly proportional to the magnetic field. So we have a time, and it's inversely proportional to the magnetic field. For very strong magnetic field, both theoretical descriptions are different. We have the Schrödinger one, this is the lattice, and we have the solid is for Dirac equation, or the Dirac description. The red one is for the initial state, the other one is for the final state. We calculated the distance, and for a very strong magnetic field, both the distance and the time depend inversely proportional to the magnetic field at the same rate, or inversely proportional to beta. We calculated this ratio, this velocity, this speed, velocity has a direction, this speed, we got a constant, and this constant, it's no the speed of light. It's a fraction of the speed of light. It's just 0.2447. And this is amazing because we use it at quantum speed limit, which is a limitation, as a natural limitation for closed system. And we got another limitation. We got another limit in which the mean position of the electron can move so fast. And well, to understand this, I show this tiny animation in which this point shows us the middle position of the electron. And that's the best result. If we compare for a huge magnetic field, both descriptions are completely different. The last value, this is an asymptotic value. When we have a vertical magnetic field, the maximum speed in this location, open and closed, is 0.7. For very weak magnetic field, both theoretical descriptions are the same. It's the weakest energy. After all, we also wanted to find which combination of eigenvalue led us to obtain the fastest superposition. Just for numerically, we calculated the first one analytically. The other ones, it's completely 0.07, the last result. But for another point, we calculated numerically, and that was so difficult because the constant normalization depends on some factorial. And for factorial for a huge number, for a computer, normally for a laptop, is very complicated to define this enormous number. Well, we got another limitation. That means that we have a very small magnetic field. The maximum speed of this evolution can be is a fraction of the speed of light. It's not a speed of light. So we can conclude that the Dirac equation is more robust, is the best way to explain when we have a very small magnetic field. And on the left side, we just for keeping, just for academical purpose, we use the information of the equation. We have a particle superposed with an antiparticle, and if you make this and we express this kind of proposition the same as before, an homogeneous expresses the energy, we can calculate the quantum speed limit, the minimal time evolved. We got another react like as before, but the maximum speed of this location looks like to be the half of the before, but it's not related to half because to show that this result is the half of before, I have to show analytically that this is just divided by 2, but I don't know. It's a numerical result, and constitutively, this is quite similar to 1.5 as before. So as a conclusion, we can express a connection between an upset space, which is related to the quantum speed limit, and how the minimal time evolves to one state or one state to another one, and making the connection with our real space, with the three-dimensional, in this case, b-dimensional, in which the electron open and close, is the middle position. And this kind of connection, well, was our first conclusion. The second one, I just noticed that the faster superposition is those that have a zero angular momentum. And the final conclusion is the Dirac theory brings more exact description of that kind of systems. And well, that's the work was published last year. Fortunately, according to the quantum speed limit, what's the minimal time to evolve to one state to another? This article I sent it, and we received our answer in less than 30 hours. It's so fast, but it's not a quantum speed limit. And finally, thank you so much for your attention.